Hello students, welcome back. In the previous video, we talked about two algebraic operations of vectors. One is vector addition and the other is scalar multiplication. Here are the computational formulae. Vector addition, we simply add up x coordinate, y coordinate, if necessary z coordinate separately. For scalar multiplication, we multiply a scalar or real number k to each component, to x coordinate, y coordinate, if necessary z coordinate, separately. They can be visualized like these, through parallelogram law. And then here is the graphical justification. How do we get the x coordinate of the sum? Blue x1 and red x2 put together, that gives you total horizontal. How about the y coordinate here? Blue y1 and red y2. Add them up and I'm going to get total vertical. That's the visual justification. How about the scalar multiplication? Here's a visual justification. Oh, it's k equals to 0.99, too close to 1, so I cannot really see anything. Okay, k is about 1.5 approximately speaking. So red is stretched by 1.5. And then we do the same thing to x coordinate, do the same thing to y coordinate, y direction. And if we have z coordinate as well, we have to do the same thing for each coordinate. And that's basically what this scalar multiplication is all about. And that's what we already discussed. Now let us talk about another operation. It's called scalar product. Previously, we multiplied vector times scalar, and then we got vector. This time, vector times vector will turn out to be a scalar. Here's a definition. V1 dot V2 is equal to magnitude of V1 times magnitude of V2 times the angle cosine of theta. Interestingly, we have another alternative form. Simply multiply the x coordinate, y coordinate, and add them up together. As a matter of fact, let me do some extension here as well. Just give me a moment, please. Okay, and then let me put z coordinate as well. Okay, in that case, what do we have here? Plus z1, z2, and that's how you calculate the dot product or the scalar product for 3D vectors. It's easy. Multiply x coordinate, multiply y coordinate, multiply z coordinate. If they're higher dimension, multiply them, and then add them all up. That's basically it. Okay, all right. What's the relationship between one and the other? Let's begin with the first expression. Let's answer a question, why cosine? That question is fundamental, answering the next question. How are these two related? Okay, all in good order. Let's answer why cosine first. Well, here is the visual explanation why. Look at especially the first picture. Look at this green right triangle where V2 is hypotenuse. And this direction, which is highlighted in thick purple, is V2 cosine of theta. And you can see that is the contribution of this red vector, V2, in the direction of V1, blue. How about the other? That's perpendicular. It does not push toward blue one way or the other. So V2 sine of theta does not do any kind of contribution, nothing. V2 cosine of theta is how much V2 contributes to V1. And this is a similar thing. V1 contributes in V2 direction by V1 cosine of theta. Same kind of geometry. That's why we do cosine. Okay. Now, how does that help us? Let's work out this picture. V1, V2, and then V1 minus V2. We form a triangle, and the angle is theta, and we are looking at what? Cosine of theta? Okay, we are interested in cosine of theta, so let's work out the law of cosines. Remember law of cosines? Opposite squares equal to adjacent squared plus adjacent squared times, well, this quantity. But that final quantity is nothing more than the dot product. V1 dot V2. This part. So in this expression, we can apply some algebraic manipulation, flip this part away to the other side, and then divide by -2, and then appropriate simplification. This is what we get. Detail is left to the students. And then apply the magnitude formula, the Pythagorean. Square and square root cancel each other out. Again, Pythagorean, but square and square root cancel each other out. In short, we get this. And then some further algebraic manipulation, break of all those complete squares, take those like terms, simplify away these common terms. In the end, we get what we want. The detail is left to the students. If you took 1600 with me, then the chance is you must have done it already, because I usually write this in the final project. Exceptions, of course, exist. For example, in COVID's shortened semester, I skipped these. Okay, let's do some examples. Find the angles between these two vectors. Okay, let's find the angles. So what computational formula do we need? Well, that's what we need. So that's where we start. And then let's find out what cosine of theta is. V1 dot V2, we need some space, divided by the absolute values, the magnitudes. Okay, what's the numerator? X1, comma, Y1, isn't it? X2, comma, Y2. That's the numerator. And let's see. This is V1, so this is red. And this is V2, this is blue. By the way, why am I doing this? Let me expand the font. Okay, that's a lot easier. And that's square root of x1 squared plus y1 squared times x2 squared, y2 squared. And this is red, it's coming from V1. And this is blue, it's coming from V2. And in this particular case, what do you get? 2 comma -4, -1 comma 2. Put those in there. Let me take one more. x1, y1, x2, y2, divided by the same thing. Okay, because this is the dot product computation. Multiply x code. Oh, whoa, excuse me. Okay, alright. According to this definition, I have to type it like this. As a matter of fact, what I typed in earlier is the version we are going to be using from next week. Sorry, okay, here. Multiply x coordinates together, x1 and x2, and multiply y coordinates together, y1 and y2, and add them up, and that's the dot product. That's the scalar product that goes to numerator. And the denominator is magnitude and magnitude. As a matter of fact, here's the computation. Put all those and then run your computation, and what do you get? -1. And cosine of theta is -1. What kind of angle is it? It's 180 degrees, pi. So the angle between these two vectors is 180 degrees. They're pointing toward the opposite direction. Well, here's a visualization. If you do something similar to these two vectors, this is what you're going to get. Take the dot product, and then magnitude, magnitude. But you don't really have to worry about the denominator because numerator will turn out to be 0. So what we get? Cosine of theta is 0. We're talking about 90 degrees. These two vectors are perpendicular to each other. And here's a visualization. Here's a little bit more general case. Whenever you have dot product is equal to 0, we have to have perpendicular vectors or orthogonal vectors. That's another term. And then parallel vectors, that's when cosine of theta is plus or minus 1. Plus 1, same direction. Minus 1, opposite direction. So one vector is constant k times another vector. And when theta is 0 or cosine of theta is plus 1, this k is positive. And when cosine of theta is -1 or theta is 180 degrees, opposite case, in that case this k is negative. That's about it. Let's see, is there any other examples that are worthy? Nice exercise. See if these two are orthogonal. So take the dot product between this one and that one, set it equal to 0, and find out x. Parallel, this one is constant times that one, and then solve for x. Or take the dot product and set it equal to 1 or -1, and then find out x value. In any case, you can do it. The detail is left to the students. After all, this is 3000 level course. So, all right, the final topic here, some properties of scalar product. We have to have this symmetry or commutative law, and then we have to have this distributivity, and then the sort of associativity of scalar multiplication. So scalar multiplication is scalar times vector, and then scalar product is vector times vector becoming scalar. So they are not exactly the same. A little bit confusing, I'm afraid, but you have to get used to it. That's the widely accepted, universally accepted term. If you take the dot product of itself, then you're going to get absolute value squared. Yeah. Here's the definition. And if V1 and V2 are the same, then this thing is just absolute value squared. And cosine of theta, angle is 0, so cosine of theta is 1. So we get absolute value squared. That's always positive. And the worst possible is equal to 0. That's when we have 0 vector. The last property of a 0 vector, again, pretty straightforward. Well, the proof of these can get a bit tricky, but believe me, we are going to come back and do all these, and we're going to do those in next week. As a matter of fact, the majority of them will be homework problems. Alright, we are done with this section as well about scalar product, and we are done with section 2. We have a little bit of time left, so let's have a bit of a digression. Vector function part is not really related to linear algebra. It has a lot to do with vector calculus or multivariable calculus, Math 2730. That's why it's here. This notebook was taken from that 2730 and also 2424. That. Anyway, let's have a little bit of digression here because we have a bit of time left. Okay, here are some examples of vector functions. What is a vector function? We simply take two functions, x of t, y of t, and pair them together to make a vector function. If you have x of t, y of t, z of t, then just triple them and make it a 3D vector function. That's about it. Here are some examples of vector functions. And what if you have both x and y are linear functions? In that case, we have a linear graph. And here is a visualization. As t changes, x of t, y of t represent the position vector, which is represented in red here. And that's changing as time t changes. The result, trace of moving particle, so we end up with a curve. In this case, the curve is line. Next example is a conic section. This is an example of an ellipse. Well, enough time? All right, so let me show you a little bit more interesting example. Just beautiful to look at. I took it from Stewart's textbook, as a matter of fact, so the credit goes to Stewart. And everything here is coming from sine and cosine. They're all periodic, and that's why we have a closed curve. Let's slow down a little bit. Again, the same thing. Red vector is p of t, and that's a position vector. X of t, y of t, horizontal and vertical position. And the result is trace of moving particle, and it turns out a parametric curve. I named it as flower because, well, it kind of looked like flower. Next one, I named it butterfly. This one, I made it myself. The picture kind of looked like a butterfly. Again, x of t and y of t are coming from sine and cosine, so everything is periodic. Therefore, we have to have a closed curve. Okay, so much for examples of vector functions. As I told you earlier, before discussing vector functions, I did it only because I had a bit of time left. We're not going to deal with vector functions in this course.